Hello everybody, this is the introduction video to energy and work. So what is energy? Energy, on a simple level, is defined as the ability to do work or cause changes in a physics system. Exactly what this change or work means depends on the form of energy that we're talking about. Throughout the study of physics, you'll come across different forms of energy, and this includes kinetic energy, potential energy, thermal energy, which is also known as heat, acoustic energy, which is also known as sound, electrical energy, chemical energy, and finally nuclear energy. The similarity among these energy forms is that they're all concerned the ability to do work and cause changes in the system that they are involved in. In this introduction video, we'll discuss the concept of kinetic energy as well as potential energy. Kinetic energy is the energy of a mass in motion. It is given by the equation half times by the mass of the object times by its velocity or speed squared. And the unit for kinetic energy, as well as all other forms of energy, is joules, which is abbreviated as J. It is important to note that all forms of energy, including kinetic energy, is a scalar quantity, which means when you're doing calculations, you only need to supply the number and the units without any direction. Suppose you have a car resting on the ground without any motion, that is, its velocity is 0. In this case, the kinetic energy of the car is also 0 joules. And when this car is moving, it will have a certain amount of kinetic energy that's equal to half times by its mass and its velocity squared. In the equation, we can see that kinetic energy is directly proportional to its mass and its velocity or speed squared. That is, when either of these variables increases, so when an object becomes more massive or when it travels at a faster speed, its kinetic energy will also increase. Graphically, this is represented by two different types of graphs. The relationship between kinetic energy and velocity is a parabolic graph because kinetic energy is directly proportional to the square of velocity. On the other hand, the relationship between kinetic energy and mass is represented by a straight line because kinetic energy is directly proportional to just mass. This is important to recognize because this tells us that velocity of the object has a greater effect on its kinetic energy compared to its mass. Calculate the kinetic energy of a 5 kilogram mass traveling at a constant speed of 10 meters per second. So its kinetic energy is given by half times by its mass times by its velocity squared. This is equal to half times by 5 kilograms times by 10 meters per second squared. This gives us a value of 250 joules. Since energy is a scalar quantity, we don't need to supply a direction. The concept of energy is associated with the ability to do work, and therefore the term in physics work done is defined as a transfer of energy when a force is applied to a mass when it moves in the direction of the force. Suppose a horizontal force is applied onto a mass on a horizontal surface. Now this force is likely to cause the mass to travel towards the right, therefore giving it some form of kinetic energy. The amount of energy given to the mass as a result of this force is given by the work done equals to the parallel component of the force vector times by the displacement of the mass that's due to the force. The parallel component of force means that the force vector must be in the same direction as the displacement of the mass. Since the displacement of the mass travels to the right, then the parallel component of the force is also horizontal, directed towards the right. In cases where the horizontal vector may not be parallel, we need to resolve the force vector into its horizontal and vertical components by drawing this right angle triangle. And by doing so, we can find the parallel component of the force vector. So here we have the parallel component of the force vector divided by the original force itself, which is the hypotenuse of the triangle. This is equal to cosine theta, which means the parallel component is equal to the force multiplied by cosine theta. This is why the work done can also be written as the force multiplied by the displacement times by cosine theta, because the force and cosine theta gives us the parallel component of the force vector. Let's go through some examples on work done. A 20 Newton force is applied to a box on a frictionless surface. How much work is done on the box after moving 10 meters? Now, as we discussed before, the force applied onto the mass must be parallel to the displacement. In this case, the mass moves to the right by 10 meters, so the 20 Newton force is already parallel to the 10 meters. So the work done is equal to the parallel component of the force multiplied by the displacement, so 20 newtons times by 10 meters, which gives us a work done of 200 joules. A work done of 200 joules means that 200 joules of energy has been transferred onto this mass as a result of the 20 Newton force. And this 200 joules of energy is likely to be in the form of kinetic energy, as the mass will be moving. A 20 Newton force is applied to a box on a frictionless surface at an angle of 30 degrees above the ground. So now we have a scenario where the force applied is not parallel, is in fact at an angle. So the work done equation is equal to force times by displacement times by cosine theta. The force applied is 20 newtons times by, again, 10 meters for the displacement times by cosine 30 degrees. This gives a work value of 173 joules. Again, in this case, this means that the 20 Newton force applied at an angle of 30 degrees has transferred approximately 173 joules of energy onto the mass. As we saw in the previous examples, the concept of work is related to the mass's kinetic energy when you apply a force to it. When you're doing work on a mass in motion, the energy is transferred to the mass in the form of kinetic energy, which means that this will increase the mass's kinetic energy. Algebraically, this is expressed as the following equations. The work done, which is the total amount of energy transferred onto the mass, will be equal to the change in kinetic energy. The change in kinetic energy is defined as the final kinetic energy minus the initial kinetic energy. The final kinetic energy is half mv squared, where v is the final velocity, and the initial kinetic energy is expressed as half mu squared, where u is the initial velocity. This is of course assuming the mass of the object is staying constant. M and m here are the same value. The only thing that's changing is the velocity of the object. So the work done causes a transfer of energy into the object's kinetic energy, which results in an increase in its velocity or speed. Let's have a look at an example. A student pushes a 10 kilogram box on a horizontal surface. The box's speed increases from 1 meter per second to 3 meters per second over 5 seconds. How much work is done on the box by the students? So we can see that the box has increased its speed from 1 meter per second to 3 meters per second over 5 seconds. So we can find the change in kinetic energy. This will give us the work done. The change in kinetic energy is also equal to half mv squared minus half mu squared. The mass of the object is 10 kilograms and the final velocity is 3 meters per second. So square that minus half 10 kilograms times by its initial velocity, which is 1 meters per second squared. The change in kinetic energy here is 40 joules. This is also the amount of work done on the box. This question can be done using a different method. We can also find the work done by considering the force applied on the object, multiply its displacement due to the applied force, times by cosine theta. We can find the force applied by considering the mass of the object times by its acceleration. This is Newton's second law. The acceleration of the object is given by its final velocity minus the initial velocity over the change in time. This is 3 minus 1 divided by a total of 5 seconds, which means the acceleration is equal to 0.4 meters per second squared. The applied force is equal to 10 kilograms multiplied by 0.4, and this is equal to 4 newtons. Now, before we can find the work, we need to calculate what the displacement of the object is during this time when the force is applied. To do this, we need to go back to one of our kinematic equations. That is, u equals to ut plus half at squared. S is the displacement that we want to find. U is the initial velocity, which is 1 meter per second. Time is 5 seconds, plus half times by the acceleration, which we found originally, which is 0.4, times by time again, squared. This gives a displacement of 10 meters. Now in this case, we have to assume that the force applied is parallel to the displacement, which means that the cosine theta value here is 1, as theta is 0. So going back to our work equation, we can calculate the work now by timesing the force, which is 4 newtons, by the displacement, which is 10, times by cosine 0, which is 1. And this also gives us a value of 40 joules. So you can see that using the two different methods of either finding the change in kinetic energy or by considering the force and displacement, we arrive at the same amount of work done, which is 40 joules. Now, clearly, in this scenario, using the first approach, which is considering the change in kinetic energy, is far easier as it involves less calculations. Work can also be done against the mass in motion, which decreases its kinetic energy. This means that work does not always need to increase an object's kinetic energy. It can be done so to decrease it. In this case, algebraically, the work done is equal to the negative change in kinetic energy, and this will simplify into half mu squared, which is the initial kinetic energy, minus half mv squared, the final kinetic energy. Now let's look at an example where work can be done against the motion of an object. A 5 kilogram box moves along a horizontal surface with an initial speed of 10 meters per second. The coefficient of kinetic friction between the box and the surface is 0.3. So this is the value of mu, 0.3. What is the speed of the box after it moves 8 meters? So this is displacement. Now we have a box which weighs 5 kilos and it initially moves to the right at a speed of 5 meters per second. Due to the friction between the surface and the box, it experiences an opposing force in the opposite direction, and that is, of course, kinetic friction. The kinetic friction is also given by mu multiplied by the normal force. Now, of course, in this case, the normal force acts upwards, perpendicular to the surface, and in the same vertical axis, we also have the weight force of the object acting downward. Since the box is moving horizontally with no acceleration in the vertical axis, we can say that the sum of the vertical forces, that is the normal force and the weight force, is equal to 0. The net force in the vertical direction is 0. So this means the magnitude of normal force equals to the magnitude of the weight force. This is useful because we can say that the kinetic friction is now equal to mu multiplied by mg. The value of mu is 0.3 and the mass of the object is 5 kilograms multiplied by the acceleration of 9.8 meters per second squared due to gravity. This gives a magnitude of friction of 14.7 newtons to the left. Finding the magnitude of friction is useful because we can use that to calculate the work done by friction over a certain displacement. This is equal to force times by displacement times by cosine theta. The force of friction is 14.7 and the displacement traveled by the box during this time is 8 meters. And cosine theta here is actually 0 degrees because the force vector of friction is also horizontal, which is parallel to the initial velocity as well as the displacement of the box, which is towards the right. So here cosine 0 gives a value of 1, which means the work that's done by friction against the motion of the box is 117.6 joules. Now, since friction acts to decelerate the box, this value of work is the amount of energy that is taken out or transferred out of the box. Algebraically, we can say that the work done by friction is equal to the negative change in kinetic energy, which is half mu squared minus half mv squared. So 117.6 is equal to half times by 5 times by the initial velocity, which is 10 meters per second, minus half 5 kilograms times by v squared, which is what we're trying to find. This gives a final velocity of 7.3 meters per second to the right. Now you can see here the final velocity is smaller than the initial velocity, which means the kinetic energy of the box has decreased during this time. And that should make sense because we said that friction is doing work against the motion of the object, which transfers energy out of the box. and this is the reason why its velocity decreases over the displacement of 8 meters. Now let's talk about potential energy. In contrast to kinetic energy, potential energy is the energy associated with the mass of an object's position or condition. Now, exactly what the condition or position refers to depends on the type of potential energy. This can include gravitational potential energy, electrical potential energy, and elastic potential energy. These are some of the main types. In this introduction video, we'll only talk about gravitational potential energy. Gravitational potential energy is the energy of a mass's position in a gravitational field. A gravitational field is a region around the mass where objects experience an attractive force due to gravity. The best example of a gravitational field is that of Earth. Objects with mass that's inside the gravitational field of Earth, which includes me and you, and the object around us, experience an attractive force known as gravity towards the center of Earth. And gravitational potential energy is the energy associated with the position of any object in the gravitational field of Earth, for example. Gravitational potential energy is also known as the work that can be done by gravity, or the total amount of energy that can be transferred due to gravity, or the weight force of an object. So we can use work equals to F times by S to say that work is equal to the weight force multiplied by the displacement that is covered due to gravity. Like all other forms of energy, gravitational potential energy is also a scalar quantity with the units of joules, and it is represented commonly by the letter U and equals to the mass of the object multiplied by the value of gravity, which on Earth it's an average value of 9.8 meters per second squared, and multiplied by the height of the object from the ground. When an object with mass m is at a height of h meters above the ground, the value of U is simply 𝑚GH. When this mass is on the surface of Earth or the ground, then the value of U is 0, because gravity can no longer do any work on this object as it is already on the ground. Since we know the value of U at a given height above the ground and also on the ground, we can also find the change in this object's gravitational potential energy. And this is equal to mg multiplied by delta h, which is the change in the object's height. When an object moves from a higher height to a lower height, this is associated with a reduction in its gravitational potential energy. Vice versa, when an object is moved to a higher position or higher height from the surface of Earth, this is associated with an increase in gravitational potential energy. What is the gravitational potential energy of a 2 kilogram mass 15 meters above the surface of Earth? So this is easily calculated by U equals to 𝑚GH. M is 2 kilograms, G is 9.8 meters per second squared, and the height here is 15 meters. And this gives a value of 294 joules. This is the total amount of energy that can be transferred due to gravity if this 2 kilogram mass was to be dropped from 50 meters down to the surface of Earth. Another way of understanding what gravitational potential energy is that this is literally how much energy potentially can be transferred by gravity or the weight force of the object if it was to fall from a height of 50 meters down to the surface of Earth. What is the change in gravitational potential energy when it falls to a height of 5 meters? Well, the change in potential energy is equal to 𝑚g∇h, the change in height. The mass and the value of g remain constant, and the change in height here is the final height of 5 meters minus the initial height of 15 meters. This gives a value of minus 196 joules. The reason why there's a negative here is because the height of the object has decreased. It has gotten closer to the surface of Earth, which means its gravitational potential energy decreases as well. Now, in physics, you'll come across this common term called mechanical energy. Mechanical energy is the sum of kinetic energy and potential energy. And remember that potential energy can refer to different types, which includes gravitational potential energy. Most commonly, mechanical energy refers to kinetic energy and gravitational potential energy because most objects will be found in a gravitational field, like that of Earth. So for any object that's on or close to the surface of Earth, we can say that the mechanical energy, which is the total energy, equals to its kinetic energy plus its gravitational potential energy. And algebraically, this is given by half mv squared and 𝑚GH. Let's have a look at an example of mechanical energy. Calculate the total mechanical energy of a 5 kilogram mass when it's at rest 20 meters above the surface of Earth. So mechanical energy, that's called the ME. This is equal to its KE plus U. When the object is at rest, it's not moving, so its velocity is 0. That means it has no kinetic energy. So KE is 0. Its gravitational potential energy is given by its mass, 5 kilos, multiplied by G, which is 9.8, and multiplied by the height of 20 meters. And this is 980 joules. What about the mechanical energy 2 seconds after it was dropped? Well, we need to first find the velocity of the object in order to find its new kinetic energy. We can find this by using one of the kinematic equations, V equals to U plus AT. V equals to 0 plus the acceleration of gravity. Again, we use 9.8 here because we're assuming there's no air resistance. If there was air resistance, the acceleration will be different because weight force wouldn't be the only force acting on the object. Time is 2 seconds. The final velocity of the object is 19.6 meters per second. Now, we also need to find the displacement of the object during the 2 seconds because it started off at 20 meters, but obviously after 2 seconds, it will be at a different height above the surface of Earth. We need to find this new height in order to find the object's new gravitational potential energy. We can find the displacement by considering another kinematic equation, that is ut plus half at squared. U is 0, like we said before, plus half times by 9.8 times by 2 squared. And this gives me a displacement of 19.6 meters. So the object here started at a height of 20 meters and it has traveled a displacement of 19.6 meters, which means the new height will be 20 meters minus 19.6, which gives a 0.4 meter displacement above the ground. So this small height here is 0.4 meters. This means the mass has almost reached the ground, but not quite yet. So we can find the new mechanical energy by considering its new kinetic energy plus its new gravitational potential energy. Its kinetic energy equals to half multiply the mass multiplied by V, which is 19.6 squared, plus its mass times by 9.8 and multiply its new height, which is 0.4 meters. And this gives a value of 980 joules. Now, I want you to be aware that when the mass was at rest at 20 meters above the ground, its mechanical energy is 980 joules. After 2 seconds, it was dropped. Despite having a different kinetic energy and gravitational potential energy, its mechanical energy is still 980 joules. I discuss why this is the case in the next video on energy and work on the topic of the conservation of mechanical energy.